Next speakers is Professor IR Dr. Taksiah Majid. She's a Dean of School of Civil Engineering and also coordinator of Disaster Research Nexus University of Science Malaysia. I think one of the significant contribution by her is she was the past members of Technical Committee in Development of Malaysian Standard for Wind Loading for Building Structure, MS1553. Today he will have a present about a topic of effect of overhang on the pressure distribution of low-rise building roofing system. Just for the informations, in Malaysia, the overhangs roofing system is common. I think more than 80% low-rise building in Malaysia have a overhang roof system. And the numbers of failure is quite higher due to non-engine. I think Prof. Taksiah will explain more in their keynote session. I have, if my time, we have another 2 minutes, but Prof, maybe you can say some welcoming note from you before you, and after that you may just proceed with your presentations. Welcome, Prof.
Okay, thank you very much, Dr. Noram-san. And very good morning to Professor Chow, Professor Tamura. First of all, I would like to take this opportunity to thank the organizer for inviting me to this special online session. It's very unique. It's the first lifetime we have this online conference of NCWE 2020. Yeah? Ladies and gentlemen, as explained by Dr. Noram, myself as a coordinator for Disaster Research Nexus, or known as DRN, in University of Science Malaysia. DRN was established in 2009 and until now is almost 11 years in terms of establishment of the DRN. Allow me to proceed to the next presentation. But before that, I would like to acknowledge these my team members, Engineer Dr. Shahruddin. I think he presented last 2 years in NCWE 2018. Dr. Noram-san, okay, the chairperson for this particular morning. I have Dr. Siti Atika, who asked the question just now on the wind tunnel. Dr. Farah, Dr. Hairul, all the team members are here with us in this particular session. Okay, actually I'm live from Civil Engineering Department of the University of Science Malaysia in Engineering Campus. So we are here, my room is somewhere here, okay, in Engineering Campus. So today we have a bright and nice weather, okay, in this part of Malaysia. Quite hot, and we just have a heavy downfall this morning. Yeah? My presentation will touch on a little bit of background of what we have carried out a research work on wind-related hazard in Malaysia, and the motivations behind the research work, and also the introduction of the low-rise buildings research work that we carried out under the DRN, and last but not least, the conclusions. Ladies and gentlemen, you have listened to Professor Tamura and Professor Chow, which is the world expert on the wind tunnel as well as CFD. So I think I like the last slide of Professor Chow. He mentioned between the wind tunnel versus the CFD. Okay, so in this particular diagrams, you look at this photo, actually, this is one of the major damage to the roof cladding due to the strong windstorm occurred in northern part of Penang on the 30th June 2018. Incident happened during the constructions. So you can see a major roof blown out of these particular buildings, okay? And this is during constructions. And of course, if you look at the detail of this, you can see that this have caused a lot of cost in terms of repair, But because it is during construction, then the repair cost mostly covered by the insurance. Okay, basically it's like a closed case, right? But I would like to bring to all of you what happened to this type of houses. In USM, we embark our research focusing on this type of low-rise building, where most of them are non-engineered buildings. This is a typical example. We call it rural houses that experience a roof damage, which is commonly happen in a suburban area. And this is another view. So this is a view of the damaged roof systems occurred in the northern regions. And this is under the category of open terrain. For example, this is a rice field where we have an open terrain, category 1. And we can see a lot of these roof damages, and this roof have been blown up during the very strong event. And this is another view, all right, of the another event occurred in Kulim, Kedah, which is on the December 2012. We can see the numbers of roof damages occurred. All right, now I would like to share the motivations, okay? Why our groups in DRN embark on these particular studies. The first point, in terms of the roof damages, we know that it's not only affecting the rural houses, but also the engineered buildings. Okay, this has been proven based on the several photos and events occurred in Malaysia itself. Number two, even though the damage may look small as compared to the total cost of the building, which is only the roof part of the structures, but the repair cost is a burden to the owner, particularly true for rural houses. And the number of wind-related damage is increasing every year, especially during the strong thunderstorms. Therefore, we would like to find or to produce an affordable and effective solution that will improve the existing roof connection for the rural houses. Another motivation is from this slide of Professor Tamura. He presented in NCWE 2017 in Kuantan, and he shows this diagram to show how the pressure acting on a low-rise building that normally experience a large negative pressure at the leading edge in this area, if this is the windward directions, compared to the side wall and the leeward wall. Okay, so the problem arises at this leading edge area where the overhang is located for the low-rise building in Malaysia. This is where the location of the overhang normally. And for your information, overhang is a typical features of low-rise building in Malaysia, and how we can improve the overhang connection around this region, which is the leading edge. Let me introduce a basic definitions of the rural house or a low-rise building in Malaysia. So if you look at this low-rise building in Malaysia, so the rural houses in Malaysia are made of wood frame structures and mostly considered as low-rise, non-engineered building, and typically built according to the location and culture. The characteristic of the rural house in Malaysia is reflected by the presence of this kitchen house. This we call it the kitchen house, normally the extension of the core house, and also the extension unit, which is lower than the core house. Okay? This structure is attached to the core house, and the size depends on the free spacing within the vicinity of the core house. This type of structure is subjected to severe during a thunderstorm event, as mentioned by Wan Chi in 2014. This is a typical example where we have a roof being blown off for these particular buildings. And the failure of the roofing failure is primarily from the weakness of the attachment and roofing materials. Such damages are normally associated to the uplift pressure generated at the roof of the house. This is another clearer pictures. I mentioned here, elevated core house, sometimes it's landed. We also have the extension, we call it kitchen house, and it's common in Malaysia to have this type of Dutch gable roof. In the schematic diagrams, we can see that this is, if we can model this as a core house, this is the kitchen house, and we have normally the roof is leaned to the roof at certain angles. So we have a gable roof, and we also identify of this gap height. Okay, this is the gap height between the lean to the roof and the main gable roof. So our research in USM, we covers various methods. Prof. Chow, very experienced in terms of CFD, wind tunnels, as well as Professor Tamura. We work as collaborative and cumulative work to carry out, we call it a basic research, so that we can embark it further, so that we can get a better understanding of this wind behavior around this low-rise building. I will share with you some of our field survey studies where we establish a conceptual framework. And then we also have carried out the hazard map for Peninsular Malaysia, the wind hazard map. And also some compositional work using NCCFD, and also a laboratory work using educational wind tunnel test. We also have a simple airbox test and a basic static test. All this work were carried out by the team of the Disaster Research Nexus. Okay, let me forgo the first one, the field survey framework. When you talk about the field survey, normally it will time consume, it will take time, right? We have to go to the sites and to collect some data. So for this field survey framework, actually, we try to produce a conceptual framework of the wind risk mitigation for rural houses in the northern Peninsular Malaysia. When we talk about conceptual framework, there's always a research questions. There are 4 research questions that we ask, and we would like to get the answers. The first one, the research question number 1, is the windstorm occurrence influenced by months and locations? That is the first one. The second research questions, when is the highest frequency of the windstorm throughout the years? Number 3, where is the most impacted location in northern Peninsular Malaysia during the windstorm event? And number 4, what are the expert and community perceptions on wind disaster management towards risk reduction? Because at the end of the day, this particular conceptual framework will be applicable and will be used by the community that be affected at that particular area. This is an example of the sites. It is in the east north of Peninsular Malaysia. We call it the state of Kedah. So the data were collected from relevant authorities such as the Land and District Office, Welfare and Department, and National Security Council. So we gather all the data and we evaluate the windstorm occurrence. It's not that easy. It is a time, you need a lot of time to do it, but we get this much of data for this state, 212 sites. And then we also go get the data from Penang. Okay, this is the data from Penang. It's about 107 sites in total. And also we get one site, one district in Perak, the states, which is in Korean, a total of 52 sites. Okay, so based on this data, so we analyze and we get these interesting results. As mentioned, this is the results based on the data shows that most of the building in the category of building age falls under the category of building less than 30 years. And we also have a house types, which is a double story, 45%, a single story, 38%, as mentioned, is about 80% in the category of low-rise building. And we also have this terrain category. Out of 22 number of house damage. So we have the terrain category 2, which is open space in suburban area, shown here, according to the Malaysian Standard 1553, way back in 2002, and also a small portion under category 3, which is suburban area, as shown here. And then from the data, we also be able to analyze that the roof pitch were constructed between 7 to 27, what, 7 to 30 degrees. Okay, and if you look at, this is the most dominant, the 7 to 27 degrees roof pitch. And the types of roof, the most dominant is the roof geometry of gable, okay, which is here. In terms of the roof cladding types, in Malaysia, it's common for a rural house to have using corrugated, trapezoidal sheeting. Some engineered building mostly use a tile profile and asbestos. So from the finding, it shows that in this particular area, corrugated and trapezoidals are the most frequently used of the rural roofing system and the most prone to damage. In terms of a number of houses damaged by district, this is the district in Kedah. So we can see that this is a distribution. The data was collected from 2010 until 2013, right? And for Penang, this is the distributions in terms of number of years of data, and as well as the number for Korean Perak. We only managed to get one district to represent Perak. In terms of number of damage, monthly data, you can see that the number of house damage increases to the windstorm occurrence took place recorded every month, almost every one. And it was observed that the windstorm likely to occur during the March, and also in June, May to June. Similarly, pattern to Perak and also in Penang. Because Malaysia has two monsoon seasons, which is the first one, the southeast monsoon, which is normally occurred from May to June, okay, and to September sometimes. And of course, the northeast monsoon from this November to March. And at the end of this study, the framework has been developed. We call it a conceptual framework. In the framework we developed, there are 6 pre-identified factors. The first one is a wind disaster event. And then we have rural housing characteristics. We have the wind loading considerations. We have wind hazard mitigations, wind disasters, exposure, and reconstructions. This is the theoretical research framework. And later, this is the final output from this study, where we establish the conceptual framework, a little bit small, I apologize for that, but it consists of the feedback from the expert, as well as from the community, and also it covers the important factors in terms of the mitigations, in terms of the risk identifications, risk hierarchy and threats, as well as importance criteria. Now let me proceed to the next research work that BRN has done, which is the hazard map. So the hazard map basically is important in order to observe the most damages that occurs throughout the Peninsular Malaysia. This study was carried out by Dr. Noram San. Okay, so this is basically the work we involve many important stakeholders. For example, when we do hazard map, actually it's not only involve engineers, but also involve researchers, policy makers, insurance company, and so forth. In terms of the steps that we establish the wind hazard map, so we start with establish the database of wind-related damage in Peninsular Malaysia. It's related to the previous work. Number two, we construct the geodatabase, consists of all the related parameters for wind hazard parameters. And finally, we establish the wind hazard map for Peninsular Malaysia. So the basic wind site equation were used, which is based on the Malaysian Standard 1553/2002. It shows here that the V site represents the V site, which is equivalent to the basic wind speed, the wind directional multiplier, the terrain and strike height multiplier, shield multiplier, as well as the topographic multiplier. And this contribute to the extreme wind speed and also the surface roughness and the topographic effects. So in this study, we have established this, we call it terrain height multiplier, MZCAT. So if you look at clearly, the red color shows a high value of MZCAT. So it's occurring somewhere here, some red dots here, okay. And also the hill shape multiplier, the red color have a higher value. And the black dots represent the damage cases, right? Maybe it's a bit hard to see here, but I will show later more better maps. And later we'll be able to establish this V site for Peninsular Malaysia. Okay, you see this value, the high value, the red dots occurring in these Kedah states, in Korean, in Perak states, and some other places in Peninsular Malaysia. And also we're able to produce this average V site according to the district. This is the district in Peninsular Malaysia. And also the smaller sub-district, we call it Mukim in Malaysia. So you can see the zone has been divided into much smaller region. And finally, based on these damage cases, we overlaid with the V site for Peninsular Malaysia map, and we be able to produce the wind hazard map based on the basic wind speed for Peninsular Malaysia. So you can see, this is where you see the red color show the highest value. But if you go a detail in the district, so you can see clearly, and the black dots here represent the damage cases. The basic wind speed in this, the red color actually is 32.5, and the green one is about 24 meters per second. Okay, and then we move on our research, we embark on these computational works. So for computational works, we start modeling using CFD, where we model our rural houses based on the survey conducted on site. And as mentioned by Prof. Chow, CFD, we can play a lot of parametric studies. So we study the house dimensions, overhang, the gap height, the roof pitch, the position of the kitchen house. This kitchen house can be at the center or it can be at the side. Okay, so it varies. And also the terrain category. In total, there are 96 models, and this work actually done by Dr. Siti. So this is the most important parameters when we study the CFD. First, of course, we need to know the pressure coefficient, the CP. And then we will present normally the result in terms of pressure contour, and also the streamlines, and of course the net pressure. This is quite unique because for overhang, and this is one of our interests, because as mentioned, overhang is a small dimension compared to the rest of the structures. But because it's very common in the low-rise building, whatever value that normally we get from the pressure contour normally is the external value. So for example, at this overhang, when we have a pressure, okay, most cases we have a suction above it. So the net actually will be higher compared to just we considering individual pressure on this surface and on this suction surface. So this is our most interest, our focus interest to determine the net pressure at the overhang locations. Okay, this is just example, some of the results where we, based on our position of the kitchen house, we can see the streamlines along the transverse profile of the kitchen house located at the center, at the center, and this is at the edge, okay. And then this is the second, we study the parametric on the gap height. So it shows here that the gap height varies from 0.025 meter to the gap height of 1 meter. There is some difference in terms of the streamline at these particular cases. And this is the value at the overhang, 0.97, 0.79, 0.86, and 0.72. Sorry. And we also study the effect of roof pitch. So we can see that the roof pitch varies from 12 degrees to 20s, and there's a equation to 27 and 17. So you can see the variation of the pressure contour, okay, varies along the transverse profile of the house model, as well as the streamline along the transverse profile of the house model. This is the effect of the overhang. Okay, this is our interest. So the effect of our overhang actually can be seen from this pressure contour. Of course, it's very small here relative to the overall profile, but we can see the CP value. The CP value actually experience a higher net pressure at this overhang position compared to the ridge, of the roof ridge. If I can present in this way, this is the plan view of the core house. So for example, this is the gap of 0.5 meter and then the wind in the 90 degrees in these directions. So normally, we can see that the CP, the maximum negative CP at the ridge, okay, with this value is at the ridge. But this is not the true case, right? This is not the true case. When roof overhang is present, normally this is the location of the roof overhang, right? So the maximum negative CP actually is at the overhang. What I mean by this is I will show these tables. I'm taking one of the models. So this model, if you look at the pressure one and the suction, the net pressure is actually 1.8 and minus 1.8, a total in the upward direction. But at the ridge, overall roof at the ridge is actually 1.21. So actually it's higher value at the overhang compared to the ridge. And with this example, actually, we underestimate the maximum suction by 48%. And then as a group, we also embarked on this laboratory work. So we did our wind tunnel, air box test, and also a simple static test. Wind tunnel, we start off with educational wind tunnels. I know this is not the ABL. This is the educational wind tunnel located at the aerospace engineering. It's meant for the aerospace. This is the model. Overall dimensions, 120 by 80 is very small because the cross section is, the test section is small. And we have the slope and the applied load to 0, 30, 60, and 90. This is the typical test section of that educational wind tunnel, a very small. The length is only 55 by 35 and the width of 30 cm. So this is the model, and we place it on the rotating tables. Interestingly, we managed to obtain relatively similar results between our wind tunnel test and data published by Osman 2016, where he used the boundary layer wind tunnel, atmospheric boundary layer wind tunnels. And as a team, our next project, we will focus on the building I showed you just now, the IPPT Bertam, using the ABL wind tunnel, where we will collaborate with other universities, for example, IIUM in Kuala Lumpur. So as a whole, we believe that this is a good starting, and I think we will embark it further. For the ABOC test, ABOC test is basically a simple frames and instrumentation that able to produce A-type compartment. That is our intention, as simple as that. So we construct this A box where we have a wooden blocks here, and then we have a pressure inlet, and we have a local cell and LVDT, and we test two types of cladding profile, corrugated and trapezoidal, using several fasteners, screws and nail, with a different thickness of cladding, which is 0.18, 0.223, 0.35, and 0.4. So this is the schematic diagram, how we develop or construct this A box to study the static pull-through behavior of the fastener under the wind uplift. Initial results shows for the trapezoidal, the maximum fastener reaction, it can goes up to the 2,300 newtons, okay? And for the local plastic here, at the beginning here, there's the region is up to 250 newtons, and then it's move on to the local plastic deformations at this phase, where we can start see the dimpling occurred, and later we can see that the plastic dimples were extended in the longitudinal direction of the crest until its pull-through failure occurred at these positions. This is the final position pull-through failure. For the corrugated, we find out that, of course, the maximum fastener reaction is much lower. It's about 1051 in the maximums. And the linear elastic region is up to 46 newtons. And then we have this local plastic deformation occurring at this stage, about 46 newtons. And this resembles a diamond shapes. When we increase the load, of course, a sudden increase in the fastener reaction force was observed, indicating the rapid development of local dimpling until it reached the maximum value of 1051 newtons. And then based on this result of the ABOC test, we extended it to the finite element, a very simple finite element, where we try various parametric analysis using NC software. So this is some of the results. We able to capture the global deformation of this trapezoidal roof cladding, and also we have these localized deformations at the central fastener of the finite element modeling. It is interesting that even though it's a very basic finite element modeling, we able to capture the deformed shapes and the local dimpling at the fastener level. This is another modeling that we enhance we introduce some enhancement. We introduce additional strips at this end to have a look whether we can reduce the deflections. And we get interesting results that the additional strip actually work very well for the corrugated profile, and it is expected, it is reduced by 35% in deflections, and for the trapezoidal, it's reduced by 9%. And then for the laboratory work, which is the last part, the static test, we also conduct a simple static test. So this static test mainly to investigate the pull out. Okay, just now I'm talking about pull through. This is a pull out failure that we try to simulate in the roof sheeting. So in this particular static test, actually we conduct on the purlin to rafter connection. Okay, this is purlin to rafter connections, where from our field survey, we find out that this is one of the critical connections that can lead to severe damage to roofing system of the rural houses. This is the parametric studies we carry out using a single nails and then a double nails, a simple double nails, and then we have nail with metal straps, and also as simple as using nail and a jute ropes. So there are 4 types of simple and very affordable solutions. From the simple test, we are able to present the result academically, where we identified several phases from A to B and C, where it starts until the stage of failure. This is just, for example, nail and metal strap connections. You can see that there is some increment in terms of maximum pull-out forces, where it's calculated to be 249% higher compared to the single nail and the double nail. This is another result of the nail and rope connection. You can see some increment in terms of the maximum pull-out force, which is about 234%. In summary, for the pull-out forces, we can see that even though we found that the nail and straps produce the highest maximum pull-out force, but nail and ropes, even though they produce the 233% increase in terms of the maximum pull-out force, but this is in terms of optimum, we would suggest that nail and rope will be the most optimum by considering the cost of this type of connection. And nail and rope is very cheap, extremely cheap compared to the metal straps that we used. In future for this lab, actually we would like to extend our work by incorporating dynamic tests such as pulse loading to represent more realistic wind condition in laboratory scales. This is another static test carried out by one of the students, Nasira, where she embarked on these 2 types of corrugated trapezoidal, and we try to model more on these overhang roof connections at this position here. And this is the simple setting up, the test assembly for resemble the uplift force on this roof sheeting. So this is the overhang with a 150 mm length. And this is just another view of the setting up. And of course, this is our initial works. Okay, this is just one of the example of the trapezoidal roof cladding with 150 mm overhang length. And of course, from this, our initial works, we hope that we can further embark to improve the connection near the overhang by introducing additional strip and additional nails. The project is still ongoing, but I think we can be able to come up with a very simple and affordable solution to reduce the number of damages caused by this overhang. In conclusions, overall, in the effort to establish our research, it involves a various field of studies related to wind engineering. And starting from the big picture of the problem using field survey to establish the conceptual framework, we also developed the wind hazard map for the whole Peninsular Malaysia. And following that, be focusing on the overhang issue. Yeah, overhang issue, particularly for low-rise building roofing system, and rural house is one of this category. For that, and we also embark on this CFD and laboratory work to have a better understanding on the response of the overhang roof, where finally the several methods on how to improve the roof connections, which is the cladding to purlin, purlin to rafter, can be developed. And last but not least, I really welcome the collaborative, okay, from any of the universities and other institutions to work with us in these particular subjects. With that, I thank you. Thank you very much. I pass back to Nuram.
Thank you, Prof. Thank you for very good presentations and also acknowledging me. Okay.
It's all your work. It's all my dear student works. Okay.
Okay. We should open the question now. Any question can be written in the chat room, or you may also unmute your mic and able to give a live question if you want. Please, all the participants, if we have now, you can give a question now. We still have good times. I think Prof. Tamura now is. Yeah, Prof. Tamura, please.
Okay, thank you. Yeah, I enjoyed your very nice and presentation, and also the comprehensive, very good study. I appreciate your effort. And the cladding design, the most important in wind-resistant design, and your focus was on the cladding design. It is very nice. And also in wind engineering field, majority of people basically interested in how the wind load acting on the building and so forth. Such a wind load side study have been made almost maybe many people interested in that part. But you are also interested in the resisting part, performance of building. Also very important that you did such a study. Very, I think it is a very excellent study you did. I think so. Detail, when we see the details, some improvement may be possible, but I appreciate and congratulate your successful study on the roofing system.
Thank you.
And you should continue this, and also we are very happy to collaborate with your group. And for some point, you did wind tunnel test, but that may be the very preliminary wind tunnel test. So pressure tap point is not so enough for considering the cladding design. The more detailed the tap distribution may be necessary, and also CFD seems to be approaching flow. It's not realistic, but comparative study, it is possible, even such a simple simulation. So I appreciate your effort. Thank you very much.
Thank you, Prof. Tamura. I really appreciate your feedback. We are learning, Prof. Tamura.
Other question, please. Other question, please. With any other questions from the participants? I think I also like to announce that I think the chat room have announced that if possible, all of the participants on their video, we will take a moment snapshot after this. Just after this, for all the participants, and maybe you can start ready now. But from that, I think just want to share. I'm not alone here actually. I just want to share. Even okay, I have a few teams behind me. I want to. Actually, I'm not alone. I cannot have a successful session this morning without all this guy in the behind. Okay.
Yeah. Congratulations.
Okay. Okay. This is Dr. Rokia, I think. Dr. Rokia, Mr. Safwan, Mr. Hafiz, Mr. Aizat, Iron Lady, Madam Emma, okay, at the back behind, Dr. Yovan, Dr. Keril, Dr. Chin, Dr. Irwan, our big boss for this conference, Idrisan, and we all like to wish him a happy birthday today. Okay?
Oh, really?
Prof, you should give one speak, Prof, to him. The question. Okay. Okay. We also have Dr. Nadiatul. Okay. Dr. Fahayu and Dr. Putri. Thank you for all of them. I think we should give a big applause to all of you.
Well done, well done.
All are supporting at behind in terms of technicals, visuals, everything. Okay. I still open the question before we have moments and just join Dr. Lim. Dr. Lim's. Hi, Dr. Lim's. Okay. Okay, we just open, still open the question. If any questions, please feel free to ask Prof. Taksiah. If you don't have a question, okay, they have a question. They have a coming question. Okay. Okay, I will read the question. Okay. Dear Prof. Taksiah, I'm Kun, postgraduate student of University Technology Malaysia, former student of USM.
Okay, alumni of USM. Okay.
I do have a question on the overhang roof, wind load estimation for low-rise buildings. Is there any further wind load estimations can be consideration due to the accidental wind load induced by airplane landing effect, especially near to the airport area?
I thought that question supposed to be Prof. Chow or Prof. Tamura. Okay. Never mind.
Yeah.
Okay, I think it's open for all, right?
Open for all, okay.
Okay, so the airplane landing flow, downflow appear after the airplane. So especially big airplane. So after the passage of the airplane, there is some downflow. But I think I never heard about the damage due to the landing. So maybe can happen, but on the line of the landing near the ground, not so much low-rise building exists, I guess.
All right, yeah.
Prof, switch on your video. Baik, Prof Taksiah. Prof Taksiah.
Yeah, I have to stop sharing, right?
Yeah, stop sharing, but your video. Your video.
What happened? Start my video.
Yeah. Okay, disappear again.
Sorry.
Okay, now
Sorry,
I think I think we have about 51 participants online now. And
Well done.
Offline we have 15 in here. Okay, thank you very much. Okay, I change to. Okay, we are still social distancing in this room. Okay, admin, can you start capture now? Okay, so maybe you can say hi or good or thumb up for the photo session for the new norms.
Interesting. Well done.
You. I say, video dia tak masuk. Gambar you tak masuk.
Okay, capture. Okay, capture. Okay. Wait. Okay, no. Never mind. Still captured.
We couldn't hear you, Nora. We couldn't hear you.
Okay, Prof, that's okay. I think we have enough photo sessions, new norm photo session. Thank you very much for this morning session. Thank you very much for the kind support from all the keynote speakers that delivering the very best, that doing the best effort to deliver the best information to the participants. I want also to, they have a further question also, further question, it's still open. Okay, there's still further question. Also from Kun, further my question, knowing there are some airport development in Malaysia, such Penang International Airport, and also tentatively claims. This question often being raised by local authority and the neighborhood of the airport developments. Therefore, shall there be any insignificant effect to the roof overhang to the single-story building? I think I opened this question. Any of the speakers want to give a response, I think, in terms of this, in terms of the effect of the airport developments and how will be significant to the roof. In here is mention of roof overhang to the single-story building around that particular area. Is it any response from the keynote speaker? Prof. Taksiah, maybe you guys.
Okay, I'm waiting for Prof. Tamura. Okay. And Prof. Chow, never mind. To my understanding, maybe the question is not exactly on the overhang, because I mentioned overhang is small component of the whole roofing systems. So maybe it's more to the effect of the overall roof of this single-story building. I haven't encountered any study on that yet, but I believe during any construction of any new, for example, new airport, the location of the nearby resident must be taken into considerations. So there must be some certain distance that you have to, develop. So I'm sure there maybe there will be some effect, but I cannot confirm that unless a further study being carried out. That is my general feedback. I pass to the other two keynotes.
Thank you, Prof.
Yeah, may I give comment about that? So if just behind the big airplane, the small airplane get into the behind of the airplane, a big airplane, there's some accident. Historically, there's some report of the accident of small airplane behind the big airplane. But I never heard about the damage due to the airplane induced wind caused some damage to the building or residential. More severe problem is acoustic noise or so forth. Residential residents near the airport. So yeah, I think not so serious for the building damage.
Thank you, Prof. Tamura. Prof. Shah, please.
Yeah. No. I agree with another two keynote speakers, Professor Tamura and Taksiah. So my feeling is that if the airplane does not changing the flow around the low-rise building, possibly it will not cause some aerodynamic effect on the buildings. So possibly the damage not so serious. But on the other side, I think for such kind of overhang roofing, if it is very sensitive to strong wind, possibly it will be debris. I don't know how the distance between the building to the airplane. If the the overhang roof overhang become a debris and it will fly. I don't know, possibly it will be if it hit the airplane, possibly it cause some problem. So possibly near the airplane, it's not good to have such kind of very wind sensitive structure.
Yeah.
Yeah, if the airplane very close to the roof, something happened. But considering the helicopter effect surface, I think it is not so strong wind will be generated near the ground.
Yeah.
But at least I never had such a report of the damage due to wind caused by airplane.
Okay, thank you for all the keynote speaker for your kind response. And I think they have no question yet now. Maybe if you have questions, particular question, maybe you can email to the keynote speaker, Prof. Tamura, Prof. Chow, and Prof. Taksiah. And I think we will finish the keynote session in this morning. For today's, we have a long break because for Muslim, today is Friday. We have they have a Friday prayer, and then we have a little bit long break today. We will start again on 2 o'clock in the Malaysian times. But however, we will open the room session 1:45 p.m. Start at 1:45 p.m. The keynote session number 4 from Indonesia, and keynote session number 5 from Beijing Jiao Tong University. And Dr. Jovan will be the chairman sessions. Okay, without I think we will end this session this morning. Thank you for all joining the keynote session this morning. Thank you from Indonesia, from Canada, India, Vietnam. I think it's something that new norm we can have internationally in one time, and I think Malaysia is the best place to have a host online because we are in the middle range of timelines. Okay, if no further question, and I think we will start at 1:40. The room will open back in 1:45 for the keynote session number 4 and number 5. Okay, thank you very much. We close the first session of first 3 keynotes in this morning. Thank you very much. Yeah. See you again in 1:45. Okay.
Thank you.
Thank you.